Please come in. Okay, so this is your first, more or less, course as graduate students. And the name tells it all, Advanced Quantum Mechanics. I will start by having a discussion about what actually are we learning in this course? What's the purpose of this course? What do we want to achieve in this course? Okay, so we can look on the name and say advanced. Probably we're moving beyond the two courses of quantum mechanics that you had as undergraduates. Okay, does it mean that we will learn here something essentially new? Does someone have an opinion about it? No opinions. The truth is, no. Basically, from the first semester that you heard the course in Quantum Mechanics 1, you basically were exposed to the whole structure of quantum mechanics, and nothing essentially changes. Still, at the end of the day, we have here a theory that in some sense is probabilistic, is non-determined. Still, we have here all the good underlying mathematical mechanisms of Hilbert spaces, operators, whatever we want to calculate. The philosophy is similar, and nothing else changes. No new grand concepts. Truth be said, if ever you'll take a course in even more advanced quantum mechanics, let's say superstrings or quantum loop gravity, at the end of the day, the basic concepts don't change. There's adjustments. There are things that we have to deepen our understanding. There are phenomena that we have to take into account that are not represented in the ways that we have studied the first two courses. But at the end of the day, the basic conceptual understanding of quantum mechanics doesn't change. And I'll take about the first half of this lecture to understand what are these basic conceptual structures that you have studied, and what is missing. Why do we want to hear another course in advanced quantum mechanics? Okay, let's start from trying to understand what have we been doing in mechanics. Basically, can anybody describe what did you do during your high school and first year as an undergraduate in the mechanics courses? Okay, let's be more operative. Let's say I had a particle here. Okay, started from something, a particle, a ball, whatever. What are the types of questions that I was asking myself in mechanics?
What forces are acting on the particle?
Excuse me, could you
What forces are acting on the particle?
Were you really interested in the forces? What is
Well, the forces would give you the movement.
okay. You need the forces in order to describe the movement. So, what was interesting to you?
Location. Motion.
Location,
Time.
Velocity.
at some time this particle was at position x. Was that enough?
Velocity.
Or momentum? And the questions that I asked myself in mechanics at time t prime what is the position and momentum of this particle? To answer it, I needed forces or potential or Hamiltonian or Lagrangian, whatever formulation that I prefer or is easier or I fancy, I took it, fed into it the initial conditions, x and p, took into account the physics in writing down the forces, the Hamiltonian, the Lagrangian, whatnot, and I came out at the end of the day with position and momentum at time t prime. Could be mathematical difficult. I probably needed to solve some equations. But at the end of the day, conceptually, this is exactly what I did. Now, of course, a system could be more complicated than that. This is a single particle. I have n particles, I have n points that give me that I need the coordinates x1, x2, x3 till xn, p1, p2, p3 till pn, and at the end of the day, it's the same procedure. Take the forces between the particles, write down the potential between the particles, play with the, write down the Hamiltonian, write down the Lagrangian, crank up my mathematical wizardry, and at the end of the day, all these are at time t, of course. I won't write all the rest. Okay, it could be much more difficult. Could be a situation where I have n to the 10 to the power 23 molecules or particles, like gas in this room, which will make it impossible. So then perhaps I have to do something else, thermodynamics, statistical mechanics. But at the end of the day, it's the same philosophy. That's what I'm interested in. If you would stop me at every given time, I could answer in principle where is each particle, or I could describe the trajectory from going from here to here. Okay, and in this case, to have a trajectory from here to here, trajectory okay, so that's mechanics in a nutshell. Everything else, details. Could be very difficult details. Could be impossible details if I have too many particles. But at the end of the day, these are all the questions that I asked myself. Okay. You have experience with quantum mechanics. What replaces the single particle description when I'm coming to do quantum mechanics?
Electron?
Excuse me?
An electron?
Could be an electron, it could be a gluon, it could be some particles that I haven't yet detected, some dark particles that I don't know even what's it called and what are its properties. I don't care what type of particle it is. Yes,
The wave function?
exactly. I don't have these coordinates to start with. What do I have? Instead of it, I have some wave function at time t. Now, pay attention. I had x and p. I have here x. What is holy about x? What's special about x? Why did I take x and not p?
Location basis.
The basis that I chose. It's my choice. I could, in exactly the same way, write down and work my way merrily after and be happy with it, and everything that I could calculate from this guy, I could calculate from this guy, it doesn't matter. The point is I don't have x of p and psi of x and p together. If I have one, I don't have the other. And that has a very deep reason, which you know what it's called. The principle of uncertainty. Okay. I want to describe what happens at time t prime. I start with a wave function. I still have only the wave function. So how did I get from here to here?
Hamiltonian.
Hamiltonian. In principle, I could get there also through a Lagrangian. And actually, hopefully, at one of the last lectures of this course, I'll show you also how to get there from Lagrangians. But we know at the moment the Hamiltonian and this little equation. Known also as Schrödinger equation. The Hamiltonian is an operator, but this is a description. Okay, again, a lot of time you have spent on the mechanics of writing down the correct Hamiltonian, understanding what operators correspond to a Hamiltonian of a free particle or a Hamiltonian of a spin system. Mathematical problems of solving this equation. Actually, I didn't spend almost any time on the time dependent, but in principle. What did basically change between here and here?
In mechanics, you knew exactly where the particle would end at every moment. Here you have some certainty, like a chance.
Right. So I'm going back to something I said in the beginning of the lecture. I told you that quantum mechanics is non-deterministic. Right? Well, let's hold a minute. You give me a wave function at time t. I get a wave function at time t prime. Is something non-deterministic here?
Yes, because you don't know what the psi is.
No, I know exactly what psi is. Give me psi in the beginning, I'll get psi in the end. And then answer what is give me psi in the beginning in a moment. But for that, I need another state. This stage is completely deterministic. There's nothing undeterministic. I might have problems performing the math. It could be complicated. But there's nothing non-deterministic here. So, what is non-deterministic here? First clue, when I went on this trajectory in mechanics, stop me in every time, in principle, I could tell you what is x and what is p. I can't tell you at every moment between t and t prime what is psi, but I can't give you the coordinates in between. How can I give you the coordinates anywhere at any time t? No, that won't give me the. That's what. It will give me some probability to be at each. No, I'm asking you, where is this particle, electron, dark matter particle?
You can say in quantum mechanics, you don't know the You know what is the
I agree with you that in the mathematical procedure that I described here, you can't answer it. But you can answer it. How will you answer it?
measure the
Exactly, perform a measurement. If you perform a measurement, then you can answer exactly what is the position or what is the momentum, not both. So, actually, the procedure here is a bit, when I'm giving you this part of quantum mechanics, I'm not telling you the whole story, really. The real whole story asked me not to use black, not to use any color that black, but I still need here something to differentiate. I want to know what is the wave function in the beginning. I have to perform a measurement. If I have not performed any measurements, I don't know where to start. That gives me the wave function. For example, if I measured the particle is here at x naught, the wave function will be a delta function of x naught. If I try to coax out of the wave function, delta function, at t, what is the momentum? I'll get any momentum. That's the uncertainty. But when I'm doing one measurement, I'm receiving one answer. Measured location, I know it's here. Let's say I want to go and perform another measurement at t0. Sorry, t0. After performing the measurement, we'll get some other psi, which will tell me what was the result of this measurement. So if everything depends on the measurement, why do I need to describe the development of the wave function between t and t prime? For the simple reasons that out of the development of the wave function, I'm able to tell you the probability that I'll measure some definite result at t prime. I'll go on and do another development in time. again, I'll get some result. It will change the wave function. I can continue, and again, it's a probability. This develops this time evolution between t prime and t double prime. Someone knows at least the Copenhagen interpretation of what happens at each point of this measurement, what it's called? Please. Exactly, the wave function collapse. And pay attention, the collapse is non-analytic. It's not described by the Schrödinger equation. All that I can tell you about it, it's some probabilistic notion. You'll measure, you have this or that probability of measuring this result. I can't give you a deterministic prediction. I can only give you probabilistic. So basically, if I remove this measurement in the way, I will get here, most probable, a different result. Therefore, I can't go around and map you the whole trajectory. It's just not there. So basically, quantum mechanics tells me something extremely strange about the world, but you're already living with it more than a year, so very strange things people somehow get used to. That the game happens on the level of the wave function. We have mathematics to tell you how the wave function develops, but once you want to connect it with what happens in your world, and usually you measure your world. I know that you're there because a photon from you came to my eye and I interpret it as you are there. Measurement changes what happens, and basically all I can say is probabilistic notions about what is the chance of this measurement. I can't give you deterministic answers. As long as I don't measure, everything's good. I can give you a full deterministic mathematical description of the probability amplitude of the wave function. Okay, so that is in a nutshell mechanics and quantum mechanics. So what are we going to do in advanced quantum mechanics? Well, lots of things here are still missing. Missing in the meaning we don't change this picture. The picture remains. The problems start, one of the problems start when I'm trying to describe a many particle system. Okay. So you can ask yourself, come on, what's the problem? I know that instead of one coordinate x, I have here n coordinates. So I'll write my wave function x1, x2, it depends on all the positions of the particles. I write my Hamiltonian appropriately with interactions between these different particles. Now H depends on x1, p1, x2, p2, and so on. And instead of asking the question about what is the probability of finding a particle at x and p at time t psi, I will ask myself, what is the probability of finding the first particle at position x1, the second at x2, the third at x3, and so on and so forth. Why do I need a whole new course, Advanced Quantum Mechanics, to solve this problem? Well, mathematically it could be much more complicated, but conceptually. Well, I fudged something. The fact that I moved from a single particle to many particles did cause me one important problem, and I'll explain. Okay. Let me simplify what's shown here and remain only with two particles. Okay, perform the measurement. I know that I have a blue particle at x1, x2. I have a red particle, sorry, a blue particle at x1, p1, a red particle at x2, p2. And now I asked, what is the probability, what is the wave function to find that meaning that what at time t prime, what is the probability to measure x1? Well, if I perform a measurement, I only know one of them, so it's x1t. Okay. And I claim that this problem you know to solve. I don't need any additional physics or definition or whatnot to solve this problem beyond understanding that now my wave function will be a wave function that depends on x1 and x2. I don't know if you did it in the course of quantum mechanics on the hydrogen atom. The same way that you solve the hydrogen atom by defining only a single electron that moves in a potential, you can solve it as two particles, the nucleus, the proton, and the electron, and having only Coulomb interactions between them, and you can solve it easily. Mathematically, it's just separation of variables, that's all, and you get exactly the same results that you got from treating only a single electron problem in a potential. Well, one small deviation, it's not the, you'll have instead of the mass of the electron, the mass of the combined mass there, but since the proton is 2,000 times heavier than the electron, the difference would be negligible. Okay, so we finished many particles. No. The reason is that life becomes much harder, not insolvable, but much harder, if I change the definition of the problem from many particles to many identical particles. Previously, when I said I measure the blue particle at x1 and the red particle at x2, means that I have a red and a blue particle. I can differentiate between them. For example, an electron and a proton, I can always differentiate between them. One has 2,000 times more the mass than the other. One has positive, one has negative charge. So put in a magnetic field and you'll see that they move differently. But when I'm going back to the same story with two electrons, I'm in a problem. I can't tell you which one of these two particles did I measure at each point. So the story here is not that I measured the first particle in position 1 and the second one in position x2. What is the result of the measurement? I measured a particle at 1 and a particle at 2. People who paid a lot of attention in statistical mechanics have run into this problem. Someone knows on what I'm talking about?
It depends on the statistics of the particle. It's like Bose-Einstein.
No, Bose-Einstein is already quantum statistical. Gibbs. Exactly. If you want, Gibbs was one of the first who understood that something is not all right with classical physics. just because of this Gibbs paradox. And first of all, why is this not a problem in classical physics? Okay, so I measure these two particles. Now I'm using the same color because I can't tell which one is which. I measure the particle at point x1 and I measure the particle at point x2. And here I could also measure the position. There's a momentum, but let's leave it aside. I come after a minute and I measure a particle here and a particle here. Which label do I put on each particle?
Two states.
Excuse me?
Many states. Because you put they are identical. So you cannot recognize each other.
Yes, you are.
Two states.
Basically, I could say that I have here x. Let's give just to differentiate between the x. Okay, I could come and tell you you have here x1 t prime and x. Could be that the first particle is here. Could be that the first particle is here. There are two possible results. Although I made a measurement, I didn't determine which one of the two cases happened. Is it this or this? Now, in classical physics, this problem could be solved. How can I solve it, at least in principle?
One go to one point and the other go to the other.
But which one went to which?
Okay. You need to measure it to see.
Exactly. I could monitor the progress of the two particles continuously. Nobody tells me that it's not allowed. Just take a camera and film it. And then you would be able to see if this is what happened. Or this is what happened. So in classical physics, the fact that I have identical particles doesn't necessarily lead to me not being able to answer the question which is in this point and which is in the other point, because I can film them and see what happens. Quantum mechanics, no, I can't film them on the way. Yeah.
Does that mean that there is no continuously measurement in quantum?
If I put in continuously measurement, I will get a different wave function in there, right? Quantum mechanics, and that's more important than anything that you will understand in this course from here on. Quantum mechanics is always measurement, determining the wave function, continuous development of the wave function, measurement. You can perform the measurement as many times as you want, but you have to understand that that will change your result. So, no, you can't follow this on the way and claim that you solved the same problem. If I come and ask you at time t, I had two particles here and here. Where is this particle? At the end of the day, you will have to give us some answer that says there's some probability that the first one arrived here and the second there, and vice versa. You'll have to give me two scenarios because you can't determine what happened. If you insist that I go and determine, very good, but you're solving a different problem. You're not solving the problems that I'm interested in. And now, this small and it sounds not very big difference leads us to a whole redefinition of wave function of quantum mechanics and what do I find in order to get the right results. I have to say something about what happens if I switch the particles. We'll spend 2 or 3 lectures on that. Okay, that's one problem. Another problem that has connections to many particle physics is in quantum mechanics, as you have studied in the 2 previous courses. What is the probability that an electron would disintegrate and come out as another particle?
What do you mean by another particle?
Could you speak up, please?
What do you mean by another particle?
Well, an electron won't disintegrate, but take a neutron, leave it alone, and after some time, not too long, 15 minutes, you'll get there a proton and a positron. You did it. It's something that happens in nature. It's something that you have to be able to describe in quantum mechanics, right? How would you describe that?
Maybe something like back in mechanics we had this problem that we took a ball that exploded into many particles. And then we had to use some sort of way to figure how the particles move.
Okay, I have one huge problem with it. Basically, what is the most stringent constraint you have on a wave function that you have learned to handle? What's the first thing you do to a wave function?
Normalization.
You normalize it. What does normalization mean?
All the chances sum up to 1.
The chances of finding the electron at time t, if I look all over the place, is 1. It's 0. Whatever I'll do to it with your current knowledge of quantum mechanics, at the end of the story, no matter how complicated are the forces that you put on it, whatnot, if your wave function is not normalizable at the end of the story, what do you know? You made a mathematical mistake. Because you have no way to describe an electron that disappears and something else appears instead of it. I gave you something that may sound exotic, but actually you have a very ubiquitous particle. It's hitting you now million or billion of times. You have a generator of this particle that sits above your head, photons, and completely without any problem, you would say you heard it many times and it didn't disturb you. The photon was absorbed by an electron and the electron moved from this level to that level, right? From second year, actually from first year, modern physics, you already heard this story. The electron moved down in level, a photon appeared. The electron was hit by a photon, was absorbed by the photon, it went up, no photon, right? So there must be a way, if I'm starting with a wave function of the photons, to describe at time t I have n photons, at time t I have n minus 1 photons. At the moment, you don't have any way to describe it. You write a wave function of n photons. How do you describe suddenly I have n plus 1? I need another coordinate. What do? I don't have the conceptual tools to describe it at the moment. So I need something to handle particles that either are not conserved. I wasn't so worried about it when I dealt with electrons, because electrons have mass. For an electron to disappear or appear, you need a lot of energy, and you used Schrödinger equation to describe, or the wave function to describe systems at low energy, and this didn't happen, and therefore all is okay. But it's not okay. Nature doesn't necessarily behave this way, and quantum mechanics should and can describe it. Okay, so many particles is a good reason to have a course in advanced quantum mechanics, because at the moment, although at the end of the day it will be the same conceptual description, I'll have some wave function that I get from a measurement. I describe its propagation in time somehow, and give you probabilities of finding it in another configuration at some future time. All that remains. Nevertheless, I don't have at the moment the language to describe it for many identical many particles or particles that can appear or disappear. Therefore, Schrödinger equation works for electrons, it doesn't work for photons. Okay, let's leave aside many particles. Everything else is okay with quantum mechanics?
You have discrete energy levels.
Excuse me, speak up please.
You have discrete energy levels, and particles can't be in the same level if they bosons are.
That will be the result of this. That we covered. Not meaning that I explained how it works, but it's under the many particles. This meant good that you raise it. Bosons, fermions is a result of rewriting the wave function. So we would be able to describe the first and the second particles are here and here, or vice versa. Actually, you will see that the fact that you have only two types of particles, boson and fermions, is a result. It's not something that we feed the equation. We'll get it. I'll be a bit more careful in dimensions larger or equal to 3. In 2, you can have other kinds of things. But we, at the end of the day, still live in 3 dimensions, although in the lab we can create 2-dimensional systems. It's a very active field of research to see particles that are not fermions or bosons. Actually, one of the propositions for quantum computing, anyons, which Microsoft for some reason pursues, is actually built on 2-dimensional systems where you don't have necessarily fermions or bosons. So it's important, interesting, but it's still here. I'm talking about another problem. Problems that people that are not necessarily solid state or condensed matter or even optics people should be very interested. Astrophysicists.
Relativistic.
Relativistic. This equation is terrible from the relativistic point of view. Why? One derivative in t, the Hamiltonian will usually have double derivatives in x, y, and z, right? We know that that's Galilean invariant and not Lorentz invariant. Cannot be. Could be that the Schrödinger equation is a good approximation at low velocities compared to the velocity of light, but it's certainly non-relativistic. And this is something that we will have to fix. So does someone know here the simplest relativistic equation which replaces the Schrödinger equation?
Dirac equation.
Dirac. We will see from where Dirac's equation comes. Why it looks as it looks. It's a bit, well, not a bit, it's more complicated than Schrödinger equation. That's the reason that for 2 semesters, while you are struggling with understanding the concepts of quantum mechanics, no one will start with teaching Dirac equation just mathematically. It's more complicated. Just for a taste of it, instead of a wave function which is a scalar, you'll have there a wave function that has 4 coordinates. It's a vector with 4 components. Why? Because otherwise you can't be relativistic. You can't get a Lorentz invariant equation. And actually, we will see that the fact that we have 4 coordinates gives us 2 very surprising results. The fact that you are forced to have 4 coordinates there tells you that every electron must be, first of all, described as having 2 possible states. And can someone guess what are those states?
Spin state.
Spin states. Spin comes at all this mumbo jumbo on 2 coordinates, whatever that you have been fed during your courses in quantum mechanics, comes out naturally from Dirac equation. You are just forced to, if you want quantum mechanics to be relativistic, you have to pay the price of having spin. It's not the price, that is what happens in nature, but explanation. That explains 2 coordinates. What are the additional 2? Excuse me?
Just T and X.
No. I have T and
What
X.
do you mean by additional 2? Like,
Hmm?
you already have 4 components. It's like 2 for spin antiparticle.
Antiparticle. You have a positron. When Dirac got his equation and tried to understand, his first idea was, oh, I explained why you have an electron and a proton. That was a wrong explanation just because electrons and protons are very different from each other. They have a different mass. But electrons and positrons have the same mass. The only difference there is that one has a positive and one has a negative charge. And that comes out from Dirac equation. Again, no additional assumptions. It's forced on you. You just can't escape it. So just putting in quantum mechanics with the requirement that it's Lorentz invariance tells you, guys, you won't have an electron as you know from Schrödinger equation. You'll have an electron that has to have a spin and has to have a partner, a positron. Otherwise, no go on on getting a relativistic equation. So we'll spend something around 2 lectures on this problem. Okay, now just a few words. So in this course we'll study to treat identical many particles. We'll come out with the knowledge to describe systems where I don't have a conservation of number of particles necessarily, and I will know at least the beginning of treating relativistic systems, relativistic quantum mechanics. What is not in this course? Many particles plus relativistic requirements gives me QED, quantum electrodynamics, which is the simplest way to describe electrons plus photons in relativistic framework. Nothing more. Sounds simple. It's not. It's not terribly complicated. It can be done, but needs its time, which I don't have in this course. Its brother or cousin QCD, quantum chromodynamics, which describes already different types of interactions and different particles that occur within the proton or neutron, has the same, similar conceptual grounding as QED, more complicated, much harder. Again, not treated here. Not treated anywhere I described here that we are combining the behavior as the requirements of relativity plus quantum mechanics. Should have been a bit more careful. Special relativity. If I want to combine the requirements of general relativity with quantum mechanics, I'm sorry, I can't refer you to any place on Earth that can give you this knowledge. Nobody knows to do it. There were suggestions. String theories, supersymmetry, quantum loop gravity, a lot of stuff. A lot of interesting mathematics came out, let's say, from string theory. Nevertheless, a concrete theories that can give me some predictions that I can go and measure doesn't exist at the moment. So that's beyond the scope that we have now. Okay. So I gave you the motivation, I gave you more or less a picture where we are. Let's go and start to treat a system that will end up in having particles that their number is not fixed. Okay, one of the problems that we mentioned here of having a system where particles can be swallowed or appear. Okay, and to have the solution to this problem is to start from a different object than we started quantum mechanics as you have studied in the last year. As I started this course, quantum mechanics, we had a particle. Classically, it had x and t. There I don't have a way to escape the problem that if I add another particle, I have to come with another x, and if it disappears, I have to delete it. I don't know how to build such a theory. So I'm starting from a completely different entity that actually you are well familiar with, but perhaps didn't think of it. Actually, you were given hints that it's a quantum mechanical system and gives you some interesting properties, but my guess would be that very few, if at all, any of you thought of it in this way. And the system is just a chain of masses with springs between them. Why I'm telling you that it has hints to quantum mechanical behaviors? In solid state, what did you learn about the system?
Phonons?
Phonons. You told, the lecturer told you, you told yourself, you sailed it back. Okay, I have here a system with phonons. I can create phonons, I can destroy phonons. They're quantum mechanical, but specifically, you never did this treatment. It was all words. The same as photons, which is the same result of treating a system, in that case electromagnetic fields. You will get at the end of the day photons. Why don't I start with those? Just they're more complicated, much more complicated. Phonons are perhaps the simplest system of bosons that I can think about. Why I'm calling them bosons? Basically, you were told that those are bosons, but massless particles have to be bosons, and those phonons do not necessarily have mass. We'll see that you can get both massless and phonons with mass. Okay, so what is the idea? The idea is, instead of starting with a system of a point that has x and p, classically I start with a field. What is the simplest description of a field?
Field equation.
Excuse me?
Field equation.
That is what you do with it. But what is a field?
A vector?
A vector? No, I have scalar fields.
Can excite
Electromagnetic is a vector field, and that makes it more complicated. Therefore, I don't want to start with it.
contains particles, it can evaluate and create.
The simplest thing, think about, describe a field to a mathematician.
each point in the matrix have some value.
Exactly. A field is an entity that give me a point, it will return a value. Basically, it's a function. So instead of the situations that I had, and I'm still talking about classic mechanics. Particle, each point in time, I have x, I can give you a value of x and t. For each point, I can give you a value at any time. To make it equivalent. Okay, so instead of one number, I have infinite numbers. You want to describe a field, you should actually give me infinite numbers. You can sometimes extrapolate between the points or give a function that will give this value, but in principle I can put any real x into this function and get a number out. Instead of one number, infinite numbers. Now, don't know how many of you did also your first degree in mathematics, but I'll keep it simple for physicists. Continuous functions are complicated and physicists run into problems while handling it. It's not easy to handle. Therefore, sometimes instead of looking on a field that has to provide me with an infinite number of values for each point x in the real, instead of x I have just an uncountable index. It's still an infinite number of numbers that I'm supplying you, but it's countable. And usually, any times that we're doing a calculation in field theory, in order to avoid running into too much problems, it pays to start to think of it in this way, perhaps take it at the end to a continuum, but okay, so what is the field that we are thinking about? I'll draw it in one dimension. this is a field that I want to quantize. Okay, actually this is a full system, not only the field. What will be the field? Can someone guess?
The values in 1 through 4.
Can't hear you.
The values inside the 1 through 4.
Well, let's see what happens here in this system. Say I move some of them, so at each time the deviation from the equilibrium position. Okay, so basically it's a discrete field. For the first one I have this deviation, for the second this, for the third this, for the fourth this. Okay, give me an index I, I'll give you a deviation. Okay, this is my field. A very complete, very clear type of field. And basically, all we have to do here, from the classical point of view, is to write a Hamiltonian. And in principle, I can go give me Ks, give me an initial condition, and I can give you the whole description of the time development of this system. What we would want to do, and this is the first step in field theory, quantize this problem and solve it. Not too complicated, not too terrible, and basically gives you an intuition on everything that we'll need to know about field theory. One-dimensional, no polarization, which we have in photons. Very, very simple acoustic phonons for those who this term means anything. The simplest problems that we can solve. It contains already everything that we need to establish an understanding what is a quantum theory that gives you the possibility to move from n to n plus 1 to n plus 2 particles. Because this system can contain, in principle, 0, 1, 2 to infinity phonons. Okay. Mathematically, what we will need to do this problem, we will get, and that will be in the next lecture, we'll see that basically we will have here an ensemble of harmonic oscillators. And therefore, in the exercise, I guess it will start at 6, you will get a refresher about harmonic oscillator. Most important, the creation and annihilation operators. That will be our main mathematical tools that we'll need here, and I will assume that you know it. Whoever feels that he is well versed in this subject and doesn't need, you can leave at this point. Whoever thinks it would be a good idea to hear about it some more and refresh it, please stay. Thank you.
Thank you.